Hey, let's talk about encryption and authentication routines that we use in computer science. This video is part of a series of several. We're going to talk about classic encryption that was used in ancient times. We're also going to talk about the modern encryption algorithms, DES and AES, and how they work. We're going to talk about private keys and public keys, and also hashing. So these are all critical concepts to understand in computer science and in computer information security. In this video, we're going to talk about modern encryption algorithms called AES and DES. So if you're into computer science and cryptography, this is for you. My name is Shad Sluter, and I teach at Grand Canyon University. We're going to talk about DES, which is the Data Encryption Standard, and the AES, which is the Advanced Encryption Standard. So these algorithms have been the standard of encryption for organizations like the NSA and anyone else that wants to hide their data. So it's a critical part of the computer science curriculum that you should understand if you're a software developer. So DES and AES were both developed to solve the same problem. In 1971, IBM was the inventor of this algorithm called DES. It gradually became insecure and crackable as computer software, or as computer hardware I should say, grew more and more powerful. And so in the late 1990s, the government, the NSA in particular, decided that they needed to have an improved algorithm. And so they put open a worldwide search and took ideas from 15 different groups. And the winning group was this pair of scientists or mathematicians from Belgium. And at 30 years old, they have created something that has been a standard for now over 20 years. So these algorithms are known as what's called symmetric ciphers. You would have a single password or key that would encrypt your document. And then that same key is going to unlock the document. So that key is obviously important. The alternative to symmetric encryption is called asymmetric encryption. And this is a far more recent invention. For centuries or even millennia, the standard for encryption was symmetric encryption. But more recently, asymmetric encryption is what a lot of communications are on the internet. So this is how it's different. We have two keys if we are going to take an encryption on a document. One key is used for closing the lock, you might say, for encryption. And then the other key is used to decrypt. So if you could imagine that you have a lock that accepts two keys. So the public key can be used to encrypt your document. This can be shared with anyone in the internet. As a matter of fact, it should be shared. And then the private key to unlock the document is private to yourself. It's also private to the person that is unlocking your document. So each person gets a private key. So the type of encryption that we're talking about today is the symmetric type, where you have a single key to lock and unlock your document. Now, the algorithm we're working with is called a block cipher. So let me explain what that looks like. Let's say we have a secret message. It's written in plain text right now, and we want to encrypt it. So a first step is to convert that ASCII code, or the plain old letters, into a hexadecimal idea. Or we could put it into binary format, either one. But let's use hex because it's so much shorter to write. So you can't read that, obviously. It's just like machine code. But that's what it means when you put it into plain text. The next step in block cipher is to split your chunk of data into blocks. And you notice that I've chosen all of them to be equal size. Now, each algorithm can pick its own size block it wants to work with. So I've only got, what, four different collections of hex bytes here. So the blocks are much bigger than this, but it gives you an idea of what a block looks like. Now, then we go through a for loop in our algorithm. We say, for each block, we're going to do an operation. We're going to take a block of data and plus the key. So your key is like your password, and we'll combine them together and put them through the algorithm. So I'll picture this algorithm as a blender because it is there to obfuscate, it's there to blend, it's to mix up the data so it becomes unreadable. So what comes out the other end then is a block of ciphered text. And so it's the same size as what went into the algorithm, it's got the same number of bytes in it, but it's scrambled. Now, when you're done, you will also have this key that's left over. It's a kind of a remainder of a math problem. And you take that key and you send it back and combine it with the next block. So each block gets its own unique key. The first block is the key that you provide. Everything after that is a computed key. So the key is literally key to how secure the lock is. So AES comes in 3 flavors. You have 128, 192, and 256. And those numbers indicate the length of the key. So in the least secure model, you have a 128-bit key that goes in, and then you blend the data. Now, if you want to be higher security, you do 192 bits, and the highest security is 256. So you might ask, why would we not just use 256 every time we want to use encryption? Well, the problem is probably with speed. Those longer keys make the algorithm run slower. And so for right now, 128 seems to be a sufficient encryption length, and so it is an unbreakable code. So if you're into math and to algorithms, this will be a very interesting section of the lecture. Otherwise, sorry, just stick with me. So how does AES work? So here's a graphic outline of what we do. So we take a plain text block and then we add a key to it. We blend them together. We're probably using XOR, the operator. And then we go through rounds. So we'll probably go 10 times through a loop, maybe 12 or even 15, depending on which key we're using. And then we have 4 steps that do obfuscation. That means blending or scrambling. And then when we're done, we have a final output. Now you need to understand what the operation XOR means. So XOR is like one of the Boolean operations in computer logic. So you're familiar with AND and OR, but what's XOR? So XOR means we will have a 0 if both A and B are 0. That's the result. If either A or B are 1, then we will have a XOR as a result is 1. However, if both of them are 1, then the resulting answer is 0. So that's XOR. So 0110 is the truth table for XOR. If we wanted to do 2 bytes of data and do an XOR operation on them, we would put them in a column format like this. And so the first column has a 0 and a 1. So one or the other will result in a true. And so for each column, we go through and compare the results, and at the bottom we have the XOR answer. So that's understandable in this example, and you'll have to see that we'll be using that a lot in our algorithm. Let's take a look at an animation of the AES algorithm and see how it works. So we have it right now, we look at this algorithm as a black box, the Rindahl encryptor. So we put in some plain text, add a key, and out comes an answer. But how does the black box work? And that's what we're going to show here. So first of all, we understand that the input state here is a block of bytes, or hex code. And then we add a cipher key. Now that cipher key can be just a random number that we provide, or a phrase, or some kind of data that we initially start with. That's your password, essentially. Now, each block is going to be operated on in the encryption process. So let's go take a look at the first step here. So we get into the encryption process. We are going to take the state, which is this little yellow block here, this is the unencrypted code, and add a cipher key. And this little plus circle means XOR. We'll add this into the initial step. Then we're going to go 9 rounds through this process here, and we're going to scramble the bits every time we go through here. And by the time they're done, we will have a completely encrypted file. Okay, so what's inside? What's the 4 steps that are inside the blender operation? Well, it's called subbytes, ShiftRows, MixColumns, and AddRoundKey. Let's see how that works. I've got some graphical pictures here, so it makes it more understandable. So first of all, there's subbytes. So the yellow block on the left is the unencrypted text. We haven't done anything to it yet. Then we have what's called an S box, or you might call this a lookup table. So you can see that each row is a number from 0 through F using the hex code, and then each column is also labeled from 0 to F. So let's say we take the first block of data, 1, 9. And if we were to take the first digit, 1, we would select row 1 in our table. And then column 9 is going to locate D4 in this lookup table. So you can get this lookup table on Wikipedia and just copy it and see how AES works. So now we've got 1 block done. Well, repeat this process, go through every item in your block, and now we have a completely substituted piece of data. On to step 2 now. So this is called ShiftRows. Well, this is pretty easy to see in graphical. We can say we're going to take each row and shift it by 1 hexadecimal place. So we'll take 1 and move it across to the right side. On the next, we're going to rotate 2 bytes, and the last one we rotate 3 bytes. And so we're just scrambling things by shifting the rows around. On to step 3. In step 3, we're going to mix up the columns. So we're going to take a column of data and then we're going to multiply it by a specific matrix. And so this matrix here, as you can see, is just matrix multiplication. So if you don't understand matrix multiplication, go look it up and then you'll see the result here. So if you were to multiply this matrix by this column, you're going to get a completely different result. It's another math formula. So we'll do this for each of the each of the columns, and now we've got ourselves step 3. Well, step 4 comes up now. We're going to add the round key. So the round key is like this produced value that comes from each round. What are we going to do with that? Well, we're going to take a XOR operation on the round key and do an XOR with each item or each column in our block. And so now we've got ourselves a whole bunch of new data again. So more scrambling. Now, what are we going to do? We're going to do this 9 rounds. So 9 rounds goes through here. We're going to do all of those operations. We're going to do the start, the subbytes, the ShiftRows, the MixColumns, add the round key. Now that round key, as you see, changes each time we go through. So that round key is a computed value based on the previous round. Well, we keep going. We go 1 through 9. And when we get to the end, we finally have our final result, which is the same length, but completely randomized. Well, it's not random, but it's completely uncipherable, you might say. So we have ciphertext. Okay, let's take a look at the key schedule. That's the last item here. So what do you do with a key? Well, if we start with a basic cipher key, that's the one that was given to us at the beginning, then we start by building on the previous key. So we're going to just shift, we're going to do some subbyte lookups, and now we're going to add another row. And so we are forming a new key to go into the next round based on the previous values of the keys. So no two keys are ever alike. So we go through, we compute all these keys differently, and we actually have a unique password then for each round. So returning once again, this is our process. We're going to go 9 rounds through our process, and we come up with an encrypted piece of data. This animation that I created was made with a tool that you can download. It's a free tool that it teaches you all kinds of things about cryptology. Very interesting if you're into that thing. So look at the link and download it. We'll do some more work on the encryption. We'll create some of our own examples of using the AES algorithm to encrypt our own documents. But for now, that's all we've got for the video on AES.